Hi, I'm a researcher in the deep learning team in Microsoft Research Redmond. And my research is actually in the intersection of natural language understanding and natural language generation. I do a lot of language generation, text generation, long-form text generation, and I do use reinforcement learning methods for several NLP applications that I have worked on so far. In this talk, though, I'm going to be talking about only one of the applications for the interest of time, touching on human-computer interaction. And I just want to thank all my collaborators here. This work wouldn't have been done without them. Okay, so what we want to do is build these intelligent agents that can actually communicate with the human. And we do use these tools in our everyday lives. They can understand language. They can talk back to us. So there's like this bi-directional dialogue happening between these devices and the human. So this is good, but they're still devices. Our environments are really not that still. Like we walk around, we just go upstairs, downstairs, like we live in rooms. So we would like our agents to act like we do. In today's technology, we can actually do this. We have these robots, these agents that can, we can just pan out the room and define these action spaces for them. They can actually do really delicate stuff, like carry these surgical equipments, if this is at hospital, for instance, and much better than humans do. But what we want them, two things. One is maybe communicate with us in natural language. That would be awesome. And also, we would like to, if we do train these, we would like to take them and put them in other environments, like, for instance, an agent trained in like hospital environment and put it in a warehouse and to actually adapt to its domain. Can we do these? Can we train agents that can actually work best in an unseen environment? So, in this talk, rather than talking about like all these RL methods that we have used, I'm going to only talk about one task focusing on these problems, and one of which is this visual language navigation task. And I'm going to talk about some of the challenges of this task and some of the methods we used to approach this task, which was like self-supervised imitation learning. I just want to note that the definition of self-supervised imitation learning, which I will be giving details, might be different than the way you're used to. I also want to touch on a little bit of a non-published work on navigation and dialogue, which is situated and bidirectional. Don't worry, I'll explain all of this in the next slides. Okay, so just to motivate, our goal is to build intelligent agents that can do two things: communicate with people, understand this natural language, and also understand the dynamics of this perceptual environment. And the alignment of the two would actually be really beneficial, enormously beneficial for the situated context, like models that we build for the situated context. So I keep saying like grounding, language grounding in situated environments. So what is it really, you might be asking? So there's probably like one of the outliers here that does deep learning and NLP, I suppose. Maybe Hal is one of them. I define it in very simple. It is building an alignment, language grounding in situations, building an alignment between linguistic symbols in language to the perceptual experiences and actions. So here's an example. So we have systems like we have search engines that can understand, we can render images that say, or map a noun phrase to this image. Because we know what a dog is, we have these classifiers that can actually know and bring back the images that relates to this noun phrase. We also can identify verbs very easily. But if you look at this verb phrase, climbing on a chair to reach a switch, in order to explain this, you need three different images. You need to explain what climbing is, reaching a switch. Reaching might be like two. You'll need those the right two images. So you can think of the first two as passive, the last is dynamic. So what we really want is to model this dynamic and to align it with these tokens in this language so that we do understand, these agents that we train has some sort of an understanding of their environment such as this. Okay, so this is the ultimate goal. So what we're trying to do is, so here's a scenario that we are very interested in. So we're thinking a HoloLens, like a user wearing a HoloLens, a human wearing a HoloLens, trying to do a task, and then the agent seeing what the user is seeing, the environment, guiding the user through finishing this task. For instance, the agent might say, "Oh, you screwed it too hard," or maybe the user needs clarification. Like we need to build these agents that can communicate the user into finishing this task successfully. So this was the goal this summer with 4 incredible interns. We worked on building or approaching towards achieving these goals together with Day, Bill Dolan, Sudha Rao from NLP and robotics background folks at Redmond, with the goal of building these interactive agents that can actually have dialogue in multi-turn dialogue. Obviously, because these are unpublished work, I won't be talking about this, but I'm going to talk about the previous work that led us to work on this task. And it is based on this vision and language navigation task. To be able to achieve that goal, we need a data set. So this task introduces a data set. So the task is building an agent that can navigate in 3D real environments that can follow natural language instructions. So this is actually not that easy task because you're combining the natural language processing, robotics, vision, and maybe some more research together to train just one agent that can understand language. What I want to stress out here is that this is actually a really hard task than it seems. So first I'd like to start with telling you about the environment and the data set. Okay, so the data set comes from this company called Metaport. This Metaport company has these digitalized images inside of the houses. So they take this, like you can see, there's a camera over there. That's a Metaport camera. Takes 3D images, like panoramic image sequences of images. To sort of digitalize inside of houses, like super rich people can actually go in and look into these houses before they buy them. So they recently released this data set. It's a huge, one of the biggest data sets out there. It contains a lot of information. For instance, you're seeing a house on the left upper part, right, left. And you see those green dots? Those are the panoramic. So I'm actually showing a bigger image here that shows an RGB image, the depth, some of the objects in the house. Like I said, this is a very rich data set, and because it's very interesting because it's like panoramic images, so you can like look, like you have the feeling of looking around. So it basically enables us to build a simulator. So, the researchers, Peter Anderson et al., took this data set and created a simulator out of it by combining each of these dots and creating a huge graph, which they called it navigation graph. So they constructed the simulator where by taking each path, so like any point in that path is a panoramic image, and then you can describe, like choose randomly at 2 different points and create a path between them. So what they did is they generated a data set by taking any path from A to B, and they ask human annotators to describe how an agent would go from point A to B. They asked like multiple different, for any single path, multiple annotators so that they will have a rich set of data set. And the task is to teach an agent that can take this natural language instruction, which is in the form of that, like you're seeing an instruction example down below, and like see if this agent can go to the destination. Again, this is a very challenging task because from going from this point to 6 steps ahead, you can choose any like a large number of paths, and the language might be really uncertain. And also like what I'm showing here on the left is an example of the simulator. So the agent sees at any given, like every time it takes an action, so instruction is given beforehand. So it's given this instruction. It's not parsed into sentences, so it's not like instructional step-by-step language. And at any given time step, there's this panoramic view. The agent needs to take an action. So as you can see, there are like glares in this image, which is really introduces some noise. There's also noise in the language as well. The language is uncertain. So like you can define going from here to over there by defining, going from over there or like going straight. So there's uncertainty in the language too. That's why I keep saying this is a really hard task. So we want to train these agents that can take actions. The actions are predefined. There are like 6 different actions going forward, backward, upstairs, downstairs, because these are like inside houses. These are 3D real houses. And so interesting thing is that, so we talked about these are like human language and also noise in the images. Given this data set, what we wanted to build is obviously an agent that can take these natural language instructions, but we wanted to focus on these challenges of this task. I want to introduce 3 different challenges. One of them is cross-model grounding. So what is cross-model grounding? So given this is a panoramic, not panoramic, like bird-eye view of the house. There's an agent and a destination, and the task is to go to the destination. So the agent is given an instruction, and usually the agent is just like responding to this location at random, and then it has to just has to follow this instruction to go to the destination. In order to do that, it needs to ground this language into this 3D image where it only sees this local panoramic images. It doesn't see, actually, because it's partially observable, it doesn't see the entire, doesn't know where the destination would be. So we're going to have to teach this agent to be able to follow this instruction so that it can actually go to the destination. Another one is an ill-posed feedback. So what it is, so I'm showing you two different scenarios. In one scenario, the agent follows the instruction and reaches the destination. In another one, it doesn't actually do well. It just randomly walks around, still goes to the destination. So the success ratio here is whether the agent reaches that destination 3 meter within the 3 meter radius. If it is a little bit above 3.1 meters, it's a failure. This is actually opposed because both of them actually success, even though the second one just randomly walked. Okay. What we really want is to teach this agent to follow this instruction rather than doing this random walk. In this year at CVPR, we published this work. What we did is we focused on obviously grounding the language, natural language, on this visual context using reinforcement learning and self-imitation learning, which I will be telling you in the next few slides. So we introduced this reinforced cross-model matching model. What it does is it takes an instruction and communicates with this environment at every time step, and then it takes an action. And then it generates a trajectory of actions. And it's at any given time step, when it decides to stop, it gets a reward from the environment. And the reward is the success rate, 3 meter radius of the target. But we have not actually talked about instruction following. So we do get the instruction as an input, but we are not forcing the agent to follow this instruction. So the way we train this agent to follow this instruction is by introducing this matching critique. Matching critique has this cycle laws, which measures to what extent this instruction and the trajectory it followed matches. I'm going to talk about that in the next few slides. And then together, we train this reasoning navigator by optimizing through this extrinsic and intrinsic reward. And then this constructs this cross-model language, reasoning path for training this agent. Again, there's only 2 modalities. So what happens inside this navigator? Well, we have this trajectory encoder. It's like an LSTM model. It knows about the state at every time step. So it gets, what it does is there's an attention model over each panoramic images. So M is the number of the images in one panoramic feature view. And then the internal state of this trajectory encoder is updated based on this, whatever the image it sees at any given time step. It also has an attention mechanism over the language encoder. It's just, you can think of it as like any sequential model, RNN model, so that it gives, so we can extract the context feature. We also want to combine the vision and the language together to have another attention model. What it does is it actually tells us where to look at in this instruction, so it doesn't actually forget what the instruction, and then you attend the language part based on what you see at that time. And then the action predictor is just a MLP layer which generates an action, a discrete action. So what happens in the matching critique? So what I talked about that in the reasoning box. Now I'm going to talk about the matching critique, which gives us the intrinsic reward. This part is actually very interesting because what it is doing is it takes the instruction. We take the instruction, we give it to the reasoning navigator, which generates the trajectory. Now we want to enforce that this trajectory matches the instruction. So how we do it? So we built this matching critique encoder-decoder sequential model. So the trajectory encoder is just like takes these trajectory sequences, maps them into a state representation, and then we have a language decoder. It's just a language model, which is pre-trained on the training data. And this language decoder evaluates, gives a probability distribution for this instruction. It tells how much it believes that this trajectory maps to this instruction. And we use it as an intrinsic reward. And then, the training is basic. We start with supervised learning, and then we do we switch to reinforcement learning with these two rewards. Okay, so I've talked about cross-model grounding, ill-post feedback. Now I'm going to talk about the generalization. That's the last thing in this work that we did. So remember, I talked about this unseen environment. So we want our agents to behave well. It's really not that easy, and there are like methods, like for instance, imitation learning, and we did use the imitation learning in a different way, I suppose. So what we did is we took unlabeled instructions, no target. So there's we don't know where this instruction is pointing at, like the goal state. We feed it into our navigator, which generates a trajectory. That's the predicted trajectory. And then we use our matching critique to get a sort of a probability of what this instruction, it believes that this instruction matches to this trajectory. And we only use the ones that we believe are strongly aligned. And then we put them in our replay buffer, like the way we train our algorithms. And then, so what it does is, it actually sort of, we found in our experiments, is it learns a better policy through its good trajectories that it observes from an unlabeled data set. All right. Okay. So what we found is that if we do use this in the imitation learning algorithm plus the reinforcement learning with this intrinsic loss, we beat all these baselines that have introduced for this task. So I'm going to show you an example, a qualitative example. So on the left, you're seeing a reinforcement-only model. This is on unseen data set, only trained with extrinsic loss. So it just like turns, and it doesn't know where to go, and it ends somewhere. So when we do use self-supervised imitation learning, I have to play this again. It actually follows this instruction step by step and ends at the right location. So what I'm trying to say here is that supervised imitation learning helps. Obviously, this is one of the methods. It's cherry-picked, but I want to show you an example that it didn't work. I like these examples. So I'm showing you an instruction, an agent that used this intrinsic reward with self-imitation learning. It followed the instruction up until to the last step. here, what it had to do is it has to stop here. With this, there's a mannequin here, but it stopped like somewhere here. There are two reasons to it. One is mannequin is not in our vocabulary, so our encoder didn't actually do well. Also, mannequin is not part of the image categories that we use for extracting these images using ResNet. It's not part of 1,000 classes. So even though we get a really good intrinsic reward because the trajectory matches the instruction, the result is a failure because it stopped like a little bit further away from the target. So we need to do better at this task in terms of encoding the language. So we got Best Paper Award from this work. So this is my intern that actually did most of the work. So we beat a lot of baselines. So this work inspired us to do new things, which I will only talk about like for a few minutes. So I'm borrowing this the slide from earlier talk, where we are trying to build these agents, like in-house agents or agents that can actually help us to finish a task. But these are most of these agents are not, like they are situated, we know how to build them, but they don't know how to converse with us, or they lack, I should say, the natural language component. So we'd like to build these situated reasoning machines. And so these are like two examples. I talked about this language-empowered agents. These are bidirectional, but not situated. So I also talk about, in this talk, situated agents, but they're like unidirectional. You just give it an instruction and it follows, and that's it. It doesn't even ask you questions. What if we're interested in reasoning machines that can converse with us in a like situated environment? So we're thinking that the natural way should be through interaction. So grounded should be via introduction. So when a user or human gives an instruction, the agent should actually think, oh, is this clear? Maybe I should just like talk with the human, get confirmation. So we would like these agents to connect, not just like get an instruction while following it in this environment, but also ask back questions, clear these uncertainties with the human. So there's this natural language question answering generation part that we need to focus on in going forward. There's some work that have, like for instance from MSR, there's this agent guide interactive work that was recently published. They and Chris Broquette and Bill Dolan has led this work. There's also another work that we're very interested. Jesse Thomason introduced this very new data set that works in the same simulated environment, the room-to-room environment, but the instructions are more incremental. So there are like two agents that you need to train that in a human-to-human language that communicate to each other, and then the task is to just, given this, for instance, the goal room contains a mat, and then you're asking the agent to go to this room which contains the mat by just giving instructions, and then the agent can ask questions back. This is a very new data set, and if you're interested, we're currently looking with Jesse together at UW. There's no SOTA, so we hope that to do, apply some of the methods that we learned from the previous work into this. Briefly, for the sake of time, I think I need to close. When I talked about the situated unidirectional agents, and using RL and reinforcement learning obviously helps, especially if we add this imitation learning component, like self-supervised imitation component, so that they could do well in unseen environments. What I really am interested in, and the research should go, is the situated bidirectional tasks. There's this new task called Vision Dialogue Navigation. Maybe it's not the best name for it, but we'd like the agents to ask questions, clarify their environment with the user. And we are focusing on meta-learning methods in this case because we know how to build dialogue systems. We know how to do image captioning or visual dialogue. how do we actually use these methods and transfer the knowledge so that, that we learn from these tasks into this new task. With that, I want to take questions if we have time.
Okay, so we have a couple minutes for questions. Yeah.
I'm just curious, for those instructions, are the instructions like there's a sofa that you're not supposed to go over the sofa, go past it? Like it matters the granularity of the instructions,
yes,
right?
It does, but the simulator is not designed that you can just jump. It's actually the next point is probably going around that. So, but then the instructions, that would be actually a really good step, because the next one, the one that we're working on, there will be instructions like that. Like the agent would go back and clarify, oh, can I just, I can't jump over this furniture. Can I go around it, for instance? We're sort of introducing some common sense knowledge in there. But it's beginning stages, and I'm open to any ideas. Or if you're interested in this work, I'm here today and tomorrow as well. Yeah.
Yeah.
Very impressive paper. I was just very curious about, do you think this would be enough to have agents play games and cooperate with people using instructions in natural language? So would this be enough to create an artificial player of some cooperative game?
Yeah. Well, there's some people here who might actually answer better than I do, I guess, on that topic, but I don't suppose it is. We're only focusing on only one angle, or one domain, I should say, at this point. But some of the things that we've done here could be easily applied to game environments. Like, for instance, any instruction following. This summer, we looked at another instruction following task, which was cooking domain. It's not like game environment, but what we did is that, while cooking, the human is cooking, you could ask questions like, okay, so the instruction was white sugar. Can I add brown sugar, for instance? So if the game environment requires that you just clarify with the human, maybe the things that we've done are sort of enough to do that, but I'm guessing that there's a lot of constraints in games that you may want to tweak your models or adjust into games domain. I'm not sure. I hope it answers your question.
Okay, I think with that, let's thank Asla again, and we can take a break.